See, first one should understand what exactly is the meaning of angular momentum. When a particle is in motion, in our earlier classes, we convinced ourselves that mv bar is treated as the linear momentum term. mv bar is the linear momentum term. But moment of momentum, I'm repeating again, moment of momentum is treated as angular momentum. For example, imagine an object is moving in this direction with with a velocity v bar actually. Now at this point, the position vector is defined as r bar. So what is angular momentum of A with respect to, it is defined as L bar. It is represented with the letter L bar is defined as, see when I am writing something R bar cross something, it is moment of what? Momentum. The moment of linear momentum is angular momentum. Even this is like torque. When we are using this word, you should define this about a point O or about an axis. So, how the way you define torque about a point or about an axis, angular momentum must also be defined about a point or about an axis. Now you consider a general case. Now imagine an object is moving along this line, whose momentum, linear momentum is p bar. At an instant, the particle is located here, whose position vector is r bar cross r bar. See, in torque, determination of torque, how the way you follow some rules. Similar rules you follow here also, which means this is the line of momentum or an imaginary line along the direction of p bar. Now here is the object. You draw a perpendicular onto this line. You draw a perpendicular onto this line. Remember, if this is R and this area, see here in this case, theta refers to angle between P bar and R bar. Then if this is a theta, this is a theta, this is R sine theta. Then the magnitude of L is defined as P times this perpendicular distance. If it is F bar, I would have termed this as force R. But this is not F bar, this is P bar. So similar to that, this is the perpendicular distance R sine theta. So P is mv. mv times this perpendicular distance gives you angular momentum L. L is mvr sine theta. This is the introduction to angular momentum. Any doubts till this point? Sure. Right. Next. Now let us take a general case. Now here my introduction deals with introducing angular momentum of a point object. In fact, which is in translational motion. Similarly, I have projected an object with a speed u, making an angle theta with the horizon. And you know clearly that it follows a parabolic path. Yes, what I have shown in the diagram. You know already this point. At an instant, the projectile is here. At that instant, the instantaneous velocity is v bar and the position vector is r bar. R bar is the position vector, v bar is the instantaneous velocity. And you already know this. Earlier also we know these observations. The instantaneous velocity is given as ux I cap plus sorry, 1 minute. Vx I cap plus Vy j cap. You already know at an instant Vx is always u cos theta. లేదు చెప్పండి. అవును 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 నేను ఇవాళ 10:30కి వస్తాను. Vx is u cos theta, Vy is u sin theta minus ct. Okay, you know this already. So this I have substituted there. Vy is this. Similarly, x is equal to u cos theta into t. Y is u sin theta into t minus half ct square. And r bar is x I cap plus yj cap. And even this one also you are aware of. And I'm just questioning you again. Maybe you would have forgot by this time, but still I have written basic steps again. Vx, Vy, x, y. Now you know r bar, you know v bar. What is r bar? Amma inta late ga vaste atta r bar is equal to u cos theta into t I cap plus that x I cap plus yj cap. Clear? Please confirm once. Varun, are we clear? Next. You draw leather. Anvit draw leather. V bar is equal to Vx Vy. Clear? So what is the base? No. I am defining r bar about origin. Oh, because that I should first define. About origin, L bar is equal to r bar cross mv bar, which can be written as mu cos. Just cross product is what I have applied. I cap cross I cap 0, I cap cross j cap k cap, which means the product of these two terms, u cos theta into t, u sin theta minus gt. I cap cross j cap is k cap. Similarly, j cap cross I cap is minus k cap. So what I have done is the product of this into this plus this into this. Any doubts? So finally, after all the calculations, you will get the L bar term as minus mgu cos theta t square by 2. That is the angular one. Let me first define. No, L bar is now a function of time. Let me just define dl bar by dt. That you will get it as mgu cos theta into t. You can rewrite this as tau bar. No. So for example, if you ask any torque related observations here, I will simply say that Tau bar is R bar cross mg bar. The perpendicular distance is u cos theta into t, force into force arm. So what I have proved right now is torque is also defined as the time rate of change of angular momentum about an axis. This is another introduction to angular momentum. So how they are related? See how the way in Newton's second law you write F as dp bar by dt. In rotational motion, torque and angular momentum are related as torque is equal to dl bar by dt. Right. Now you see on what factors angular momentum depends. The angular momentum depends on point charge chosen as origin or axis. Angular momentum depends on point chosen as origin or axis. So what is a parallel axis of rotation? For example, this is axis of rotation and this is R bar and this is V bar. Use the right hand grip rule. Stretch your right hand in a shake hand mode. Set the thumb along the axis. First, align the four fingers along R dash bar in this case. Turn towards V. Now the thumb represents L bar actually. But in this case, this L bar is parallel to axis of rotation. Angular momentum is parallel to the axis of rotation. Any doubts? Anika. Next. Suppose instead of O dash, if I choose this point, totally different. Even now also you can use right hand grip. Now you see, you stretch the four fingers along the string, turn that along V, you know, this is the direction of R bar cross MV. Okay, na? This is along R bar, this is along V bar, this is the direction of R bar cross V bar, MB bar actually. Now, no longer the angular momentum is along the axis. Of course, the angular momentum will now have two components. This is the direction of angular momentum, and this angular momentum will have two components, one radially outwards, one axial, parallel to the axis. Two situations. So now, two components are there. That is the reason why when you are defining about the angular momentum term, you first define about which point you are doing this. What is the point of reference as per your observation? You first define that. Only then you proceed further. You got the point? Got the point right now? Sure. Next. So I have introduced what is angular momentum. Angular momentum of a point mass. That's the discussion right now. Now, anyone in this class, are you sure that you still have any doubts on this? Right. Let us proceed further. Now, let me introduce the next stage. What is that? Angular momentum in case of a rigid body about a fixed axis of rotation. Remember, you have a rigid body and this is the axis of rotation. If that is the axis of rotation, what happens? Let me first define you that. That is the axis of rotation. Then, you know, I'll take one element in this. I'll take one element in this. Now you take one such element here. Now whose position is Ri, whose mass is Mi. Sigma Ri bar cross MVI bar. You already know VI bar is defined as, this is the relation, first week of rotation also, relation between linear and angular terms. All right. So what happened? That I have substituted this one here. Now Ri bar cross omega bar cross Ri bar. Now in mathematics, if this is A bar cross B bar cross C bar, this is in this format. You will write this as B bar times A bar dot C bar minus C bar times A bar dot B bar. Exactly, I have substituted the same. Remember, in this case, this is a fixed axis. In case of fixed axis, omega bar is also in the same direction. Then in that case, every Ri is perpendicular to omega. Therefore, this term totally vanishes. I am repeating again. This is the axis of rotation. This is the direction of omega bar. This is the ith particle. And in this case, omega of every particle is the same. But omega and Ri are perpendicular to each other. So the dot product is 0. So therefore, finally, all these particles, the total angular momentum is given by sigma I mi Ri square omega square. And you know very well about this term. What is this term? Moment of inertia about that axis. So L bar is I omega bar. Remember, when you are writing L bar as I omega bar, remember you are writing it about a fixed axis. Now I am questioning you again. Do you still have any doubt on this? Go through that again. If you still have any doubt, please ask me right now. Are we clear? Sure. So what was our first class deals with? What exactly our first class deals with? First part of the class. The first part of the class deals with point mass. Right? The first part of the class dealt with introduction of angular momentum of a point mass. The second part of the class dealt with the angular momentum of a rigid body about a fixed axis. Now, the third part of the class, see, in fact, the major part of this week is only these three theory points. The entire week you will work on applying these things. Right. What is the next part of this class? The next part of this class deals with angular momentum in case of a rigid body with the free axis. Free axis. What is free axis in this case? Now you have a situation like this. You have a round object spinning and translating, which means rolling otherwise. In fact, it's a rolling. It won't come under fixed axis system because the axis of rotation is also in translation. Now I am taking a point O as the reference. Taking O as the reference. Now the question is, this particular point P, you have RP bar. This particular point P, you have RP bar. What do you mean by that? I am giving the position coordinates of a point in the rigid body. Right. So only that point if you want only that point, I can give you angular momentum. Simple definition: RP bar cross MP VP bar. Agreed? Hello? Agreed? Okay, right. See, please try to understand in this case, this is RCM bar, location of the center of mass. This is RPCM bar. So therefore, from this I can conclude RP bar anytime can be written as RCM bar plus RPCM bar. Now, please confirm whether you understood this step or not. Just please confirm me only that box. Have you understood that box or not? Anika, Sushmita, Rakshita, followed, right? Now, what is the velocity of point P? Okay, that's not an issue at all for me. Velocity of the point P is velocity of the center of mass plus velocity of point P with respect to center of mass. That is the deal. Now I have substituted the angular momentum of a point P. Only that point, please remember. Now I got RPCM bar plus RCM bar. Sorry, in this place I have written this term. In this place I have written this term. Any doubt till this point? Now you arrange this properly. Expand the cross part. This one cross the entire thing. This one, totally 4 terms you will get. A bar cross B bar plus C bar cross D bar. 4 terms you will get. First term is this. This is the first term. Second term is this. Third term is this. Fourth term is this. Any doubts? Akka. Right. Now the question is, see, this is only one particle's history that you are writing. You have n such particles in the system. You have understood the angular momentum situation of one such particle P about O. Don't ever forget that you are defining this angular momentum with respect to O. O is the reference, and O is a point fixed to the ground. Now I would like to take the angular momentum of all such particles. Take summation. Then again, post a summation to this term, this term, this term, and this term. Let us start with this term. So, summation to this term. Remember, just now we have done this term. Here only. Here only we have done Ri, omega bar cross Ri. We got this as L bar as I omega. Just now we have done. Which means the entire term you will get as ICM omega bar. Now please confirm me, okay or not. VPCM I will expand as omega bar cross RPCM bar. Finally, you will get ICM omega bar. Same as what I have done just before. Next term, if you permit me, remember this is a constant term. VCM bar is independent of the particle. In that case, if I put MP to here, makes no difference. Even if I take a product like this, makes no difference. But the problem is, sigma of this term is 0. Anyone in the class, tell me the reason. Excellent. This is as per the characteristic. And they put so many game punjay. 3 weeks back, 4 weeks back, మీకు పని చేయరు బొర్ర ఇంకా ఎందుకంటే మీరు ఫిజిక్స్ శ్వాసలోనే ఇంగ్లీష్ చదివినట్టు చదువుతారు ఎందుకు జీరో అంటే నేనే చెప్పుకోవాల్సిన పరిస్థితి ఉంటుంది మీకు మళ్ళీ అవునా కదా టక్కని చెప్పాడు వీడు అలా వస్తే మార్కులు వస్తాయి ఎవరో ఏం చెప్పేది మూమెంట్స్ అబౌట్ algebraic sum of characteristics of center of mass lo cheppam algebraic sum of moments about center of mass is 0. Similarly, for the third term, the summation of this ikkada rastuna reasons malli repu gurtundadu sigma I sigma p mp rp cm bar 0 because moments about center of mass sigma p mp vp cm is equal to 0. Reason is the same, differentiation of the above moments about center of mass. So basically this is 0, this is 0. And fourth term, you can't do anything with this. RCM bar cross MPVCM bar. Because this is constant, this is constant. In that case, that sigma is applicable to only M. So finally, what is happening? Out of 4 terms, 2 vanished, only 2 survived. And they are ICM omega bar plus RCM bar cross omega or VCM. Okay, so it is nothing but L about a fixed point is angular momentum about an axis passing through the center of mass plus angular momentum of the center of mass. That's the thing. What is this term called? Angular momentum about the center of mass. What is this term called? Angular momentum of the center of mass. Treating center of mass as a point mass. E3 me covered. Only with these 3, I am going to do the entire week. If we are good, then a lot of people say that, sir, I'm weak in physics. Okay. I don't have any basics in physics. Okay. Now tell me what basics is required for you beneath this to understand the topics. Sushmita, do you still believe there is something beneath this which is not allowing to understand this? Pakka? Tejaswini? Sure. Right. Boy, Satvik. Right. Now, law of conservation of angular momentum. Just now we have defined, torque is defined as the time rate of change of angular momentum, dl bar by dt. Okay, when no external force acts on the system, then what happens? When no external force acts on the system, if tau bar is 0, dl bar by dt is 0, L bar remains constant. L bar remains a constant. Angular momentum term remains constant about the axis. Now you take one simple case here. Here, an acrobat is doing gymnastics with some loads or dumbbells in his or her hand and spinning about some axis like this. Omega naught. With the hands stretched, the angular speed is omega. So all of a sudden, to increase the spin, the angular speed about that particular axis, he will stretch, he will actually draw the hands towards the trunk. Then what happens? I decreases. The result is the omega increases. Omega is more than omega naught. You can see that a lot of time in Olympics also you will see. When the girl stretches a hand, lesser rotations per second. When she draws a hand towards the trunk, then more number of rotations about her own axis. Even in swimming also, from what you call deeper, what is that you call? They will jump from certain height, diving. So in the air, the faulties, whatever that spins, how to increase the spin? He will draw the entire body towards the trunk, thereby reducing I, thereby increasing omega. This is what moment of inertia, angular momentum conservation deals with. Remember, in this case, it is a fixed axis. So I1 omega naught is a, no, you said L bar constant. So obviously, I omega is a constant. Remember, we are dealing with fixed axis. So therefore, I1 omega naught is equal to I2 omega. Okay. Now we are applying something about this. Now you take a situation like this. You have a kid standing at the edge of a disk. Did you notice this? Let ID defined as moment of inertia of the disk alone about a fixed axis. Small m is defined as mass of the man at the edge of the disk. Man moving along the edge. Or it is as same as, do you remember Planck and man situation? Planck and man situation. But that is a linear case, this is a turning case. It is actually turning with respect to the axis. So therefore, to conserve angular momentum, the disk needs to turn in the opposite sense, so that the total angular momentum remains constant, and in fact, it is zero initially. So angular momentum of the disk plus angular momentum of the man is a constant. So therefore, ID omega d bar plus mr square will treat man as a point mass, omega m bar. Now, but what is convenient for me anytime is defining angular velocity of the man with respect to the disk. When I am defining angular velocity of the man with respect to disk, then omega m bar will take a shape into this form. So with this, you will have this. A very, 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 very standard relation. Lot of times in mains type questions, you are expected to apply this formula. With this, the fundamental basics for the entire week to some extent is done. 60-70% is done. Now we will deal strictly with problems. Tell me, do you have any doubt till this point? Paka? Sure? Now let us start doing the very first problem. This is a problem from H.C. Verma. Remember, since I felt this is a difficult topic, I have given questions from H.C. Verma. Now, read the question without discussing with your friends. Imagine that this is our disk. Imagine that this is the kid. Imagine that this is the ball, which is moving with the speed u, and this is of mass m. And this is a fixed axis. If someone asks me what is the initial angular momentum of the system, disk is not rotating 0, disk part is 0, man is not rotating 0, and whereas for the ball, m, u, r. Why? R bar cross m v bar. R and m mutually perpendicular. So therefore m, u, r. This is for the ball. Now what is happening? The kid is catching this. As a whole, what will happen? Finally, I disk will have omega. Man or the kid will have omega. And the point mass or the ball will also have the same omega. As a whole, the system is rotating. Now, please confirm. This is for the disk. This is for the man. And this is for the ball after the event. Now, please confirm. Please confirm about the axis of disk. Angular momentum initial is equal to angular momentum final. MUR is equal to I plus MR square plus MR square omega. Therefore, omega is MUR by I plus capital M plus small m R square. Please confirm. Do you have any doubt in this? I taught you any elementary level problem in this situation as a first choice. If you have any doubt, please ask me. Are we clear? Meghnad. Noora, ni per Dhananjay. Clear? Right. Suppose the platform of the previous problem is brought to rest with the ball in the hand of the kid standing on the rim. The kid throws the ball horizontally to his friend. Please remember, follow the steps carefully. Suppose the platform of the previous problem is brought to rest with the ball in the hand of the kid standing on the rim. So everything is rest right now. Disk rest, man at rest, ball at rest, or kid at rest, ball at rest. The kid throws the ball horizontally to his friend in a direction tangential to the rim with a speed v as seen by his friend. Find the angular velocity with which find the angular velocity with the platform. The question is his friend is an outside observer. His friend is an outside observer, actually. If his friend is an outside observer, please tell me why should there is a change in the it's almost like the same situation. Why should I do it as a different question? Everything is the same. Reverse direction you need to go, that's all. Everything is the same. Cut, copy, paste. Now, which means L initial is 0 plus 0 plus 0. This is a disk, this is man, and this is ball. Right. What is L final? L final is I omega plus MR square omega minus. Why? Because here, to conserve angular momentum, the disk should rotate in opposite sense. So therefore, MVR. So therefore, to conserve about the axis of the disk. Law of conservation of angular momentum gives That's 57. Any doubts? Boys and girls, we are good in this question. You will definitely be good in this question. Next. Suppose the platform with the kid in the previous problem is rotating in anti-clockwise direction at an angular speed omega. Okay. The kid starts walking along the rim with a speed v relative to the platform. Also in anti-clockwise direction, find the new angular speed of the platform. Now, what is my system first? My system in this case is platform plus the kid. Agreed? Platform plus the kid. Now the question is, Li of this system initially is, now we will take anti-clockwise sense. The axis is towards us, k cap. So Li bar is I plus mr square omega bar or omega times k cap. Now, angular velocity of the kid with respect to disk is v by radius r, right? I think the radius is r. If I'm not mistaken, radius is r. So omega of the kid, just now we have derived one relation. What is that? Omega of the disk. But this is the case where initially system is rest. You are not supposed to use this relation because this you are supposed to use only the entire system is initially rest. Whereas the entire system is not initially at rest in this question. It has some. Therefore, omega for kid is omega of the kid with respect to disk plus omega of the disk. What is L final? L final is I omega disk plus mr square omega of kid with respect to disk plus omega of the disk. I omega disk. Omega disk means final angular velocity. Final angular velocity plus mr square v by r k cap plus mr square omega disk. So, law of conservation of angular momentum about axis of disk. This gives you the condition. What is that? I plus mr square omega disk bar plus mr square v by r k cap is equal to I plus mr square omega k cap. So finally what you are going to get is, this is I plus mr square omega k cap minus mr square v by r k cap divided by that's all. So simply omega k cap minus mr square v by r by I plus mr square k cap. That's it. Boys and girls, do you have any doubt? Sure. Pakka. Right. Please kindly follow right from the basics. Any doubt in this question, please ask me. Next question. Please read the question carefully. This we have done in a different style last week. Now you can apply the same thing by applying law of conservation of angular momentum. Initial angular momentum about Li is ICM omega bar plus RCM bar cross MVCM bar. That's the general formula. Agreed? ICM, what is the solid sphere? 2 by 5 mr square. It is into the plane of the paper. The sense of rotation of omega is clockwise. Into the plane of the paper. So minus omega k cap plus. So remember RCM bar cross MV bar. It is simply MV capital R. But what is the sense of rotation? O is like this. V is like this. R is like this. Now please tell me what is the sense of rotation of angular momentum of the center of mass as a point? MVR. Which direction? Into the plane. Anika, are we clear? MVR minus K cap. Remember, it is not in pure rolling initially. Okay, it initially without slipping on you just mentioned initially itself. Okay, fine. Also, V is equal to R omega. How? Rolling without slipping. Are we clear? Rolling without slipping. So now the angular momentum of this system is simply 2 by 5 mr R omega minus K cap plus MVR minus K cap. 7 by 5 MVR minus K cap. That is the initial angular momentum of the system. 7 by 5 MVR minus K cap. Any doubts? That's all. That is the total angular momentum about O initial. Any doubts? Boys and girls, do you have any doubts? Noora, much better. Ashraf, clear? Yes. Right. Next. Yes. A disk of moment of inertia given spinning freely at 3 radians per second. A second disk of moment of inertia 2 kg per meter square slide down the spindle and they rotate. It's like a common velocity. I'll just give you the description like this. This is already one. Just dropping. Now, initially, this will have omega and omega 1, omega 2 is equal to 0. Okay, that is the situation you have initially. Finally, what will happen is that Yeah, as a whole, the system will have a common angular velocity. Have you noticed the difference? So both the disks move together. But still, do you sense as the two together as a system together as a system, is there any external torque? Maybe one disk exert torque on the other, that's fine. But as a whole, externally, there is no torque. So therefore, the initial angular momentum is the same as the final angular momentum. I can say I1 omega 1 plus I2 omega 2 is I1 plus I2 times omega common. Therefore, omega common is I1 omega 1 plus I2 omega 2 by I1 plus I2. Right. 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 Now, what will happen in this case? Just try to see this. What is the expression for loss? Lassian rotational Ke is equal to final half I2 I1 omega 1 square plus half I2 omega square minus half I1 plus I2 omega common square. Correct or not? Here, tell me yes or no. Yes. So after solving this, you will get I1 I2 by I1 plus I1 plus I2 times omega 1 minus omega 2 square. Remember, if in this case, fortunately, omega 2 0. Suppose if both are in the same direction, you will use this formula. Suppose if omega 1 is in this direction and omega 2 is in opposite direction, formulas will change. In that case, common angular velocity is I1 omega 1 minus I2 omega 2 by I1 plus I2, whereas loss expression is half I1 I2 by I1 plus I2 times omega 1 plus omega 2. You just substitute whatever you want, you will get the answer for this. Any doubts? This is a very, very, very famous question. I'm not giving you this as a formula. In fact, I've done this in a problem style. Okay? Clear? Still, I have used law of conservation of angular momentum only. Next. Next question. Next question. A uniform disk of radius R naught lies on a smooth horizontal plane A similar disk spinning with angular velocity omega naught is carefully lowered onto the first disk. I'll try to explain the situation. This is a disk 1. This is a disk 2. And it is having omega naught. Actually, you know that they will attain common velocity undoubtedly. Right. How soon? So you need to find much more depth version. You don't, I mean, this is the case where it is not simply with the initial and final condition. They want even intermediate condition. So if I somewhere in between, what is happening? You study one such a layer here. One such a layer here. Let this be of radius r. Let this be of thickness dr. This is the first difficult question as per my knowledge in today's discussion. So carefully stay close to the concept. You take an element here. This element, this is the top one. I'm seeing it, the top one. It has a tendency to rotate like this at an instant, whereas a friction torque will oppose the rotation. How to calculate friction torque? See, total mg mass is distributed over pi r square. So per unit area, what is the normal reaction? This is mg by pi r square. Okay. And in this elemental area, normal reaction at elemental ring. Normal reaction at elemental ring. Dn dash is equal to dr. dr. Dn dash. So on the entire ring. So therefore, frictional torque on the entire ring is simply mu into 2mg by r square r dr. That is the force. That's all. Force. And a torque kada meeku kavalsindi. Into r. That is the frictional torque. Only on that element. Likewise, you will have n number of frictions. So the total frictional torque, in fact, I should write a minus sign also because this is opposite to the sense of rotation. So this is 2 mu mg by r square dr 0 to capital. Boys and girls, You will have this one as minus 2 by 3 mu mg by r square times r cube. This is nothing but at an instant the torque. That instant torque is minus 2 by 3 mu mg by r mu m 2 by 3 mu mg r. That is a torque at an instant. Now, all these are fundamentals. Fundamentals. Now you know what you want. I alpha is minus 2 by 3 minus mu mg r. This is a disk, I know, mr square by 2. D omega by dt. You asked time actually, right? Right. How soon do both the disks spin with the same angular velocity? This is equal to minus 2 by 3 mu mg r. M cancel. So d omega is minus 2 by 3 mu g by r. 4 by 3 mu g by r dt. Right? Initial angular velocity is omega naught. Common angular velocity is omega naught by 2. Don't ask me why. I1 omega 1 plus I2 omega 2 by I1 plus I2. I1 is same as I2. Omega 2 0. So what will happen? Omega naught by 2. Common angular velocity. So you should write this as omega naught by 2. Right. Boys, this you will get as omega naught by 2. This you will get as 4 by 3 mu g by r t, which implies t is 3 omega naught by omega naught r by 8 mu g. Please confirm. మీ దగ్గర ఆన్సర్స్ ఉన్నట్టు ప్రింట్ తెచ్చుకోలేదా 3 by 4 వచ్చిందా జస్ట్ ప్లీజ్ చెక్ ద క్యాలిక్యులేషన్ can you please tell me why there is a 2 term here because of this right sigma తీసుకొని r square by 2 d array 2 అటెల్ 4 just give me time till this point I'm absolutely correct I got the torque correct only. Torque is 2 by 3. Torque correct వచ్చింది. I have done mr square by 2 d omega by dt minus 2 mg by r. For one I am applying. Correct. Now why I got 4 here? Tell me. Why I got 4 here? Because of this 2. That should be the answer as per my knowledge. Any step deviation, please inform. Is okay for me. Here also we have done proper checking and all that correct. ఎలా తీసుకుంటాం మూమెంట్ ఆఫ్ ఇనర్షియా అప్పుడు క్యాన్సిల్ అయిపోద్దిగా టార్క్ You are applying this on one disk, actually. Okay, right. No issues. ఇక్కడ ఏమైనా తప్పు చేసాం ఒకసారి referring into R 2mg by R square RDR times R. This is cube by 3. Corrected? Sharing actually. But I'm sharing. That big. This is why I don't use this system. Right. Okay, no issues. We will work on this. I'll give clarity on this tomorrow. No issues. Let us not on this. Now you see, this is the next part of our model. Solid sphere is set into motion on a rough horizontal surface with a linear speed v in the forward direction and an angular speed omega by r. Remember, we have done the same problem previously, but rotation sense is different. Now the rotation sense is different. Now you define that this is your O. This point is O. So what happens after some time is that V naught omega naught such that V naught is equal to R omega naught. That is the pure rolling case. But in between some time, rolling, for example, I want one more case in between, or here, right, questions. Now, what is about O initial angular velocity? ICM V by R K cap actually. Why? Sense of rotation is different. Plus MVR minus a K cap. EL final is ICM omega naught. You want a linear speed actually. V naught by R minus K cap. MV naught R minus K cap. Agreed? All about O. Any doubts? Please ask me right now. I'm telling you again, sir, I don't know all these things. I don't have basics. I still find difficult. ఇది ఇప్పుడు చెప్పాలి కదా, ఎప్పుడు చెప్తున్నారు మీకు? మార్క్స్ అడిగేటప్పుడు చెప్తారు. రక్షత, ఆర్ వి క్లియర్ ఆన్ దిస్? L initial is L final. So ICM V by R K cap plus MVR minus K cap is by the way, what is ICM? It is nothing but 2 by 5 MRS. So minus 2 by 5 MR square V naught by R K cap. K cap. K cap. So from this you can write so this will become 2 by 5 MVR minus MVR K cap is nothing but minus 7 by 5 MV naught R. So K cap. So finally you can write minus 3 by 5 MVR is minus 7 by 5 MV naught R. MR by 5. So finally V naught is 3 by 7 V. The linear speed when pure rolling starts is this. I would like to add a page extra to discuss the other case. What is the case? The other case is that is the case V initially. You want the case where stops rotating. Stops rotating case corresponds to this. Fine. So L initial is L final. L initial. There are no change. Everything is the same. Everything is the same. In this left hand side of our equation is still the same. So minus 3 by 5 MVR K cap is MV dash R. That's all. That's all. Why? No rotation. Minus a K cap implies V dash is 3 by 5 V. Linear speed when కూర్చోము
rotation when rotation stops. Any doubts? Are we clear? Sure. A very, very good model. Very, very good model actually. Clear? Next. Now, the next case is again the next part of the theory which we are dealing with. This is the last theory part which is required for this. See, remember the entire week runs with one single angular momentum conservation. But entire week I have given 100 questions as assignment posted today. And you should complete those 100 questions. Last week, no one finished it. No one completed. Right. A point mass collision with a rigid body. This can be treated as a two parts. Part 1 is A. Now I'll teach till this part because my resources are not qualitative today. I'll just stop here. Right. You complete the the remaining part. Point mass collision, case A, one is a fixed axis, the other is a free axis. Fixed axis case, see, you will have a situation something like this. A rigid body in the form of rod, in the form of disc, in the form, whatever it is. But you will notice that it is hinged about a point. And a point mass moving in some direction. Here for convenience I have shown it's in a straight line path. It can even strike it in an inclined, obliquely also. Right. Then in such case, what to do, what not to do? In such a case, do not apply law of conservation of linear momentum. Why? Hinge will exert external force. So never apply law of conservation of a linear momentum because it is not applicable when there is an external force acting on the system. Next, law of conservation of angular momentum can be applied about fixed axis of rotation. Remember, you are allowed to use only about the fixed axis of system, but for whom? The entire system, point mass plus the rod. In this case, you should have an idea. System, point mass plus rod. And also, you see, unknowns will become, immediately after collision, unknowns becomes angular velocity of the rod, linear velocity of the point mass. So you require two equations. But I have given only one equation. What is that? Law of conservation of angular momentum about the fixed axis. You require one more equation. For that equation, you need to have either the information about the initial and final kinetic energy or nature of collision of the point mass with the rod. That will give you second equation. With this, you can solve. So, in case where a point mass strike a rigid body about a fixed axis, the unknowns will be angular velocity of the rod after collision, linear velocity of the point mass after collision. To do this problem, you require two equations. First equation is apply law of conservation of angular momentum about the axis of rotation. The second point is, see, when you are applying law of conservation of angular momentum, you should apply for the system comprised of the rod and the point. Whereas some information and coefficient of restitution, initial KE, final KE of the system, some information must be provided, else you can't do this. Till this point, any doubt? Next. Now you take another case where the rod is free. It is as same as I have placed this pen on the table and you are striking a point mass with that particular pen. In this case, you can apply law of conservation of linear. So what are unknowns after collision? Tell me. Common sense. What are unknowns after collision? 1. Center of mass velocity of the rod. 2. Angular velocity of rotation of the rod. 3. Velocity of the point mass after collision. So you require 3. You have 3 unknowns, 3 equations. First equation, law of conservation of linear momentum. Second equation, I always suggest to apply law of conservation of angular momentum about a point just below the center of the rod, not attached to the center of the rod. Just below the center of the rod, and that point is on the table, not attached to the rod. And third point, again, they should give us some information about the initial and final KE or the nature of collision with the given rod. So this is how we will do problems. So tomorrow we will take care of this, right? Chalo.